I prepared this talk in a Emacs scratch buffer. So if Emacs crashes, everything could disappear in an instant. I'm going to start with, I want to briefly talk about persistence, persistent allocation, and my implementation of this in the Ares PMA. I don't really need to preach to you on the utility of a single level store. We already have this. Although it's really shitty and it's limited to 16 gigs now? 8. Right, we never got up to 16, although we could theoretically. That's kind of absurd to be reaching for 16 gigs. This is working on Ver previously, like it started at 2, you got it to 4, then I got it to 8. And there are ways we could get it to 16 if we used 64-bit words rather than 32. But Urbit development has stretched back quite a long time. And when it started, when Ver was first conceived, 64-bit machines weren't even that commonplace, right? That's where Ares comes in. We're going to replace Ver because it's easier than amending Ver. We're going to clear out all of the Ver politicians. So let me just briefly, I don't need to really harp on this, but when we started doing computing, we have a word for memory. It's called memory. What is memory? It's really annoying. We have these analogies to understand computers. And humans have a short-term and a long-term memory. And so it seems natural at the moment, and we justify sort of shifting short-term memory into long-term memory. But this is just like an ugly hack. And memory should be memory. And you shouldn't really have to think or actively deliberate on what I'm going to commit to long-term versus short. Where am I going with this?
We don't know, David. Where are you going with this?
I need to look at my script.
You got to get it out of the cache.
That's correct.
Paging.
Right, so computers nowadays have volatile, non-volatile memory, but they're both memory. Oftentimes when we say memory, we think only of volatile memory. There's no guarantee that this will still be around when we crash, when we kill a process, et cetera, et cetera. And so persistence is... Where am I going with this? Joe?
Manual.
Yeah.
Persistence is
Persistence is painful. You need to serialize data and deserialize data. If you're writing a Python script to analyze something, some financial data or earthquake magnitudes or whatever, you often want to save your results. You don't want to read the original data set. It might be huge every single time you run computations on it. And so the way you currently get around this is actively persisting. You have to check if a file exists, some persistent file. read it back into main memory, page in and out, with which operating systems help with, obviously. But it's really ugly, and you would love if like an array of 64 gigs could just exist, regardless of how the process terminated, and without actively reading it into that array. This is the utility of the single level store. We have this in var, as I've previously stated, but it's limited in size. This is where the PMA comes in. So I'm moving on to number 2, persistent allocator design. Databases have aided us in this painful problem of persisting, but they're still lacking in certain ways, primarily in serialization and deserialization. Databases are fault tolerant, necessarily. Not all of them are, and it's really kind of a stretch to even call them databases. In every Linux distribution, you have access to GDB-M, which is a GNU relational database, but it's not fault tolerant. It's totally fucked. I don't know why anyone would use this. There are various hacks to add fault tolerance to GDB-M, but why am I talking about GDB-M? Nobody uses it because it's not persistent. What do people use? They use LMDB. LMDB. We don't. We do. Oh, we do. Yeah. That's right. LMDB is a persistent relational database conceived by Howard Chu. Well, before I talk about LMDB, I'd like to talk about the simplest solution to persisting data. I've already justified, in my mind, the utility of the single level store. One way to do this is by copying everything. So you could conceive that if you have, let's say, 64 gig memory arena, and when I terminate my process or it crashes or whatever, I would like everything I've stored to be present and accessible when I resume the process. You can only achieve fault tolerance ultimately via redundancy. You need a copy if the previous copy gets corrupted. And the simplest way to achieve redundancy is via copying everything. So that 64 gig arena that you'd like to persist and have available when you resume the process, you could achieve that redundancy by having 128 gigs accessible on your machine, or at least 128 gigs of storage. And you would persist this data by every time you sync or you demand what I've written must be persistent and accessible when I resume, by copying that 64 gigs over. But this is a problem primarily because you're just abusing the disk. But it's simple and easy to understand. Copy everything, and if the copy I'm currently working with gets corrupted, I fall back. LMDB, of course, doesn't do this. LMDB doesn't copy the entire database every time you sync it. It selectively chooses what actually needs to be copied. And it does this by tracking dirty pages. What data has been modified since I've last synced? And this is primarily like dirty page management. Guarantee of redundancy is sort of what distinguishes, and doing this efficiently is what distinguishes a database from just a shitty file copy. LMDB sort of eschews. I don't know if anyone's read fsyncgate. I haven't read all of it. I've read like a little bit of it. It's very long. But there are syscalls you can use to make particular guarantees about what has been written and what hasn't been written. But this is just like prone to errors and primarily, well, where am I going with that? fsyncgate. fsyncgate. Say it again. fsyncgate.
Just
Yeah.
skip it. Tell
Yeah.
us about double buffering.
I will. Yeah. Yeah. Howard Chu. That is his name, right?
Yes.
Yeah. Howard Chu. He skips all of this and he essentially does it himself, and he achieves this more efficient redundancy rather than copying everything. As I've said, that's the simplest design, by essentially keeping a clean copy, and in a modified copy, only writing what needs to be written, only writing what has changed. You don't need to make redundant data which hasn't been modified. And so LMDB achieves this with a double buffering system where each time you sort of sync the database, you switch between a particular root in the database. And you track the pages, dirty pages, modified pages, which need to be synced. I mean, the PMA was heavily inspired by LMDB. At the end of the day, it's just a B tree. Adjust. And let me write.
Can you explain a B tree?
I can, yeah. Thank you, please. Like I'm completely directionless, but I can answer questions. A B tree. What is a B tree? A B tree is like well, it's a binary tree. It's not a binary tree. A binary tree, of course, has a node and 2 branches. A B tree has n branches. A B tree is used primarily in file systems, and it's a way to effectively use disk, because at the moment with computer architecture, we unfortunately have this distinction between volatile and non-volatile memory, and we want to abstract that. We want to provide a single level store, and so we have to manage the sort of interchange between volatile and non-volatile memory to give the illusion that you have a single level store, or to actually implement a single level store. It's not necessarily an illusion. A B tree, as I said, a binary tree with n branches, and at the leaf nodes, above leaf nodes, you refer to other nodes. At the leaf nodes, you actually store the data you want to store. So in LMDB, there are different data types. It's not really worth going into, but at the leaf nodes, the data segment, or the extents to which you're tracking, store the actual data you care about, whether that's strings or integers or whatever. Those are stored in the leaves. it's an efficient way to use disk.
Put in the PMA.
Yeah, but in the PMA, we don't have different data types. We're sort of borrowing Howard Chu's ideas. Well, not necessarily borrowed from Berkeley DB, but that's a tangent. We are in the PMA.
So what's our key and what's our value of the PMA?
Yeah, right. In the PMA, our keys, in a database, you typically have a string key. And in the PMA, we're trying to abstract a memory arena rather than just serving as a value store. So a memory arena you could think of as performing a lookup on a particular address. In the PMA, that's our key, is an address. Technically it's an address offset, but it's not really necessary to get into. Our key is ultimately an address. And you can think of the PMA as managing in the background like an explicit lookup at an address. The PMA guarantees that at this address, the memory that you've written to or will read from, that's there. And abstracts that explicit lookup and makes it implicit. The values are the data you store. So when you make a malloc call, say malloc 10 and write into it, the data is, of course, the actual data you've written. The PMA, of course, is distinguished from a typical malloc API in the sense that what you've written, you're guaranteeing the persistence of. So when you malloc, you're only dealing with volatile memory. And if you want to persist that, you have to do it explicitly. But the PMA is an implementation of a single level store. And so what I've written, I'd like to guarantee is there, regardless of how this process terminates.
So what are our values that we're actually storing in the PMA?
The values that we're storing in the PMA are just atoms or cells. It's anything that.
What's the values in the B tree?
The values in the B tree?
So we talk about the keys. What are the values? You haven't said
The
that.
data.
This
Values.
disk offsets. The disk in the B tree, it's the disk offsets.
The disk offsets. Oh yeah, well technically yes. So right. In our B tree, we're storing. So we're sort of managing. You can think of the B tree, not the B tree. You can think of the PMA as essentially a manager that manages memory offsets to disk locations or disk offsets. Because the disk itself, the backing file, stores the data. But the PMA aids on shutdown and restart, getting the data that we expect to be particular memory locations there. And we do that by storing as keys the virtual addresses and as values the disk offsets. I think this is thoroughly confusing at this point, but I think I'll try to clarify.
Just go through the data structure.
The data.
Yeah, I will.
Explain the data is linear in memory. It's not linear in disk.
Yeah. In Unix, you have this call called mmap, which maps to a particular memory location a particular offset into a file or a disk location. Yeah, sure. And ultimately, all the PMA does in order to
In order to allow us to copy stuff.
In order to allow
us to copy chunks.
Sure. Yeah.
It has to allow us to have a non-contiguous mapping.
Yeah. Right.
Yeah.
Right. In order to sort of provide the illusion of a single level store in order to copy stuff. In order to provide the illusion of a single level store, I'm just gonna, I'm sorry. This
Show us the data structure.
yeah, I think I will. I think this is, yeah. I'm gonna get off the mic and I'm just gonna speak loudly. I'm gonna show you some data structures to give you, yeah.
Turn the mic off so it doesn't go kerplunk.
Yeah. All right. So yeah. I think I don't think I've sufficiently explained what the PMA is doing, but like in 3 sentences or 2 or 1, the PMA provides the illusion of a single level store. It avoids unnecessary copying of data which hasn't been modified by tracking dirty pages and doing copy on write. And it manages this memory arena, which we expect to contain certain data, by persisting that into a file and also sort of bringing that up via mmap calls into memory when you resume. And the way it does this is probably best explained via an exploration of the data structures. So at the very sort of top, we have a B-tree meta page. The meta page contains a lot of things.
Bigger file.
Is that better?
One more. That's good.
Yeah. Shift this over.
It's still not good. Not for me.
Get closer.
That's good though. That's good.
So at the top, we have, at a top level, this isn't quite the root of the B tree, but this is what we store at the beginning of our persistent file is a B tree meta page. We have 2 of these, which is where the double buffering comes in. A meta page stores a number of things, but principally it stores a root of a B tree. That root is stored here, and I think I'll probably, let's see. The meta page, it's important to realize that when you sync the data you've stored, you sort of tick-tock or flip between the meta page you're referencing as the current valid data. We also CRC32 checksum it in order to handle cases where we erroneously shut down. We were using 1 copy of a B tree, which is now kind of invalid. We can't guarantee that the data that's been written is actually there and not corrupt. Then you switch back to the old one if that's the case. So your current meta page is whichever is CRC32 checksummed. A meta page refers to a root page. Our B tree structure is actually incredibly simple by comparison to LMDB, which is a more complicated structure. Our meta page consists of a header. The header only stores dirty bit information about the children. This is where we avoid the copy everything problem. The dirty bitmap tracks which pages actually need to be copied into the persistent file. So upon write, copy on write, we mark a page as needing to be written into the persistent file, and then we actually allow the modification. The page, besides dirty bit information, which refers to the children, or in the case of a leaf, it refers to the data segments, consists of just and this is better visualized here. It consists of essentially an array of virtual addresses and disk addresses, if you could call it that. They're technically offsets. Yeah, file offsets. You can see here, I don't know if this is large enough. Here.
Blow it up more. There you go.
This is sort of a this is what a new B tree root looks like. So when you first boot up a fresh Urbit, you'll have for storage a root page, and it only looks like this. This sort of defines the bounds of your allocation space. The starting virtual address being this. These are offsets again, but you could think of them as addresses, and a file offset. And the virtual address at the end, which sets the bounds of this allocation. A file offset of 0 means that the space is free. So that makes sense. On a new root, you have this entire from 2 AAA 80 to this large address. It's 64 terabytes total, roughly. You have this as free space. If you perform an alloc into the B tree, you need to traverse a number of ephemeral structures, which I've kind of skipped over. But you'll find a file offset, which will serve at the moment contiguous, although it's not necessarily not necessary.
Yeah.
You'll find a file offset which can store your data, and you'll perform at least one insertion in the B tree. In this case, I've given the example of just 0x foo. So what this says is I alloced 16 pages. I've set the dirty bitmap, I've set the first entry in this case, because it is the first entry, to 1 to indicate that this page needs to be persisted. All of the other pages, it's not necessary to copy. And at 2 AAA 80, corresponding to file offset 0x foo, and yeah?
Shouldn't the FO in the second one just be 0 because that space is still free?
Yeah, that's true. I don't know why that's. Well, no. So yeah, the virtual. Yeah, that's correct.
Yeah. You don't need to store the end of the file offset.
That's correct,
because
yeah.
You can get the length information from the difference of the virtual addresses.
Yeah, so I think it's helpful to sort of think about what if we crashed, or what if on resume we're trying to restore our memory mapping to what it was previously. And when we walk down to this root B tree page, we see a virtual address of 2 AAA 80, and we see a file offset of foo. Further, we see another virtual address of 2 AAA 90, because that's 16 pages. And this indicates to us that we need a mmap at disk offset, or from disk offset foo at virtual address 2 AAA 80, a 16-page length. And so we do that. When you restart or reread the PMA, you walk down it and you perform all the necessary mmap calls in order to sort of restore the memory mapping as it's expected to be. Because you want to be able to access an address and write to an address without any additional layer of, say, like database access. I don't want to have to tell it to store at this key or this address. I want to just be able to write to it. And that's where this comes in. This file offset of 0 indicates that this is free space, which is to be expected because we started from a free root, completely free, and we simply allocated 16 pages. Following this, I have a free call, which is a partial free. Rather than freeing the full 16-page extent, I free 8, the first 8 pages. And you can see how this is modified. This file offset of 0, which indicates free, and extends to half the length of the original allocation. These are inserted in the B tree. I then have, that is not correct, but it should be 2. That should be
That's your FO, right?
F0x F08.
Yeah.
No.
There you go.
And this virtual address would be 0. Yeah. So I don't know if this is this clear to everyone? Yeah. Virtual address. So by freeing, I've inserted a 0 into the B tree. Again, the B tree, the point of the B tree is just to remember the arrangement of memory. And then every time you restart, yeah, question?
B tree normalized, like you have two zeros next to each other?
It does, yeah. So that was implemented what we call deletion coalescing. So when you free multiple contiguous segments, on an insert you check, and it's lazy. So it only happens when you're actually allocking rather than freeing. You will normalize. You'll free pages if necessary, and you'll shrink the B tree. But yeah, that's necessary in order to shrink the file.
When we looked at the dirty bitmap
Yeah.
thing, is that per page or
There's 1 bit per page. And
is one bit?
one bit
Yeah.
per child
Each
page.
yeah.
Oh, so that's extendable. That'll grow with your as your B tree grows.
It doesn't grow. No, it's set at 2048 bytes. So the B tree, our B tree that we use for the PMA is really wide and really shallow. So at most, it can extend at like really large data allocations. It can extend to a depth of about 4, which actually makes some of the algorithms easier because you're not actually that concerned about like deep tree traversal and simplifying that.
How wide does it go?
How wide? A particular page or?
Is it 2048 nodes?
It's 2048 bytes in order to store the dirty bit information, but each bit tells you, yeah, if that segment is dirty or not. So it's 2048 times 8. So in total, that's.
I thought it was 2048 bits.
Oh yeah, that is correct. Yeah, it's 2048
That
bits.
would be a really
No, right. It's 256 bytes. Yeah. So.
We standardized on 16K pages just to like not have compatibility problems with Mac OS.
Exactly. Yeah. And the.
In the source, it's just hard to deliver that. I'm saying the source is
It's
Yeah, so I went into this talk with like plans, well, like 2 hours ago, with plans for at least like justifying the single level store. I don't think that's necessary. I think we get the utility of that. And also like the simplest in order to implement a single level store, the simplest design, which is copy everything, to an amended, more complicated design, which is track what actually needs to be saved, what has been modified, what we know is good on disk, etc. Then I had a PMA code exploration planned. I don't think I'll get into the nitty-gritty of, there are like 5 free lists in the B tree, in the PMA. This is necessary in order to manage memory, file free space, nodes, which our nodes are stored not in any separate file, but they need their own allocation space. And we do this by just storing it contiguously in contiguous segments and expanding it, but by partitioning them. So we have to track that information as well, and those are pulled from a node free list. And then on sync, we have 2 pending free lists. Those being for the file and then the node disk free list. Yeah, I'm trying to think. So what do you achieve with this design? One, you manage to avoid any errors which might have been seen in like fsync gate by basically doing double buffering and copy on write yourself. And not relying on the kernel. Let's see. Yeah, right. I'm trying to, but what do you achieve with that? Well, compared to the VAR road system, you have 64 terabytes it's a bit less than that due to node partitions technically, of usable space. The B tree provides this sort of database that informs how to restore the memory map to what you expect. And the free lists are all ephemeral and reconstructed on what we know to be good data. Yeah, that's the design. Are there any questions, or is there anything like confusing about this, or I failed to? Yeah.
So we're going to use this when we're allocating nouns, right?
Yeah.
This is when we're allocating something noun, and we need to have a virtual address for it, that we allocate somewhere. Actually, at this, that's kind of what the B-tree manages.
Yeah.
So what is can we walk through just kind of all right, you're allocating this noun, maybe you're dropping part of it, maybe it's a list, you're taking the second part of it, you partially free it. What does that kind of look like instantiated in a B-tree operation?
Yeah, I think Edward. Yeah.
So the B tree, the reason you have a B tree is because you want to be able to copy parts of your memory space to new places on disk, which by definition makes the thing non-contiguous. So you need to store an arbitrary mapping at page granularity between virtual memory and disk. When you allocate from these free lists, you have to walk 2 free lists and find 2 free spaces. You have to be able to find enough free space on disk for your allocation, and you have to be able to find enough free space in your virtual memory space for the allocation. Once you have those 2 large enough contiguous runs of pages, you simply insert that range into the B tree, because B trees actually they're used to store keys, but they are actually the design makes them very good for storing things by index range, right? So you literally insert that from this virtual address to this virtual address is mapped to the disk offset starting here. You don't have to store the disk range because it's the same length as the virtual memory head, right? So that is what the malloc does. Is it takes stuff out of the free list and inserts it into the B tree. That's it. Free looks like essentially the reverse. You take stuff out of the B tree and stick it back in the free list. The complication comes in because what if the thing I'm freeing is stable on disk? I don't ever want to write something that's part of my current snapshot. I always want to copy it first. So I don't want to take that disk free space in particular and put it back in the free list. So this was something that was pointed out, and the solution articulated by Howard Chu in the LMPP papers, which are kind of hard to find actually, but if you can find them, he talks about for disk, you always have a free list and a pending free list. So if you are freeing disk that is part of your current snapshot, it goes in the pending free list. When you take another snapshot, so now you have a new no good snapshot on disk, you don't care about the old snapshot anymore, so things that were free in the old, that were allocated in the old snapshot that are free in the new snapshot are in the pending free list, which you now merge into your actual free list. So that's why there's the complication of all these additional free lists, and that's a high level of what allocated free look like. I mean, that the malloc routines look very familiar. Yeah. It's like pull stuff out of free list, put it in a free list, but you're also tracking stuff in the B tree, and you have this kind of 2-stage free list for the disk side only. For memory, we don't pick, right? We have 1 free list for memory, we have 2 for space for data, and then we have 2 more for space for B tree nodes. So we actually have a free list and a pending free list for space on disk for B tree nodes as well. So that gets you 5 free lists that you're juggling, right? But just be grateful Dave wrote it for you.
Yeah, I think if I have to close on something, it would just be a high level overview of this really sort of confusing look at the PMA. You can conceive of the PMA as essentially a B tree for storing memory ranges and their corresponding disk offsets, plus any ephemeral data structures necessary for a basic allocator. That's essentially just that's like 5 free lists and various like sync routines, etc. That is the PMA. The B tree itself is a modification of the LMDB B tree, but engineered for storing memory ranges and disk ranges. And on startup and shutdown, at shutdown, you sync the necessary pages that you have to sync to disk. And on restart, you only have a B tree. You look at the B tree, you reconstruct it, and you, via mmap, push into the memory arena, although you don't copy, and there's no swapping involved. Like, reading the B tree is really quick. Because we're m-mapping, we only need a copy into memory from disk when we actually try to read that data. So on restart, you walk the B tree, restore the ephemeral data structures which are necessary for allocation, and you restore the view of memory that you expect via mmap calls. This is all very quick, again, because there isn't any copying into and out of memory unless it actually needs to be performed, which is one problem with the current design in VAIR, is that getting data from disk into memory is an involved process. With B tree, we're just restoring memory as it should look without copying. I hope that's kind of clear. Yeah, do you have a question?
Yeah, so in this PMA, the ship snapshot will be stored.
In the
Yes. Yes. But you also mentioned that if you need to write a new snapshot, you will copy the whole thing, or no?
No.
Okay.
No, the entire point of this is to only copy the bits that were altered.
Okay.
At some granularity.
Right.
Right?
Okay.
And then be able to, VAIR can also do a differential snapshot, but VAIR's differential snapshot basically requires
To go through the whole thing.
no, it doesn't require you to go to do the whole thing, but it requires you to keep your dirty set. See ya, Joe. I can't let him get away. It requires you to constrain the size of your dirty set to basically available RAM plus swap. That with a arena of the size that we're targeting, you don't want that constraint. So the design constraint for the PMA was everything must be m-mapped to disk all the time. If you have data, it's m-mapped on disk. The operating system always has the option to flush it from RAM to a spot in your file, not to whatever measly bit of swap the user forgot to allocate, right? So that's the big design constraint for such a big arena, aside from just like, oh, we have 64-bit things, and we don't actually want to. So the VAIR mechanism is that when you dirty a page, you copy it into RAM, into a page mapped, we say anonymously, which is the Linux way of saying this piece of memory has no disk backing it. It's just in RAM. So if it has to be swapped out, it has to be swapped out to your swap partition or your swap file. And if you don't have one of those, well, you're host. And so when VAIR takes a snapshot, at the time of the snapshot, it does a two-step. It first copies all of the data, all of the dirty pages, to what they call a patch file that just holds the dirty pages. Make sure that is synced to disk. Then it writes those dirty pages back over the original snapshot, then it deletes the patch file. So if you start there and there's an existing patch file,
Which will
you
reapply.
start reapplying it from scratch, and that application's item code. Again, the problem is, as soon as you dirty a page, so the problem's twofold. First of all, you're copying data back and forth between two files. Secondly, as soon as you dirty a page, it no longer is disk backed, and so you are constrained in how many pages you can have dirty at a time. So if I'm trying to download, I don't know, if I'm trying to download some gigantic set of LLM things, I actually don't just need to like break that up over multiple events. I actually need to make sure that my persistence file, if I did the PMA this way, I would need to make sure that like my persistence file synced in between each one. Otherwise, the actual just dirty set from trying to like construct this thing that I'm getting over the wire in memory would just be too big, right? So the point of all this is just to keep memory mapped to disk all the time, which means if we need to copy it, we need to copy it somewhere else in the same file and immediately remap it back to the same virtual memory address.
Right. Okay.
And that is what the B tree is tracking. I copied it somewhere else, but I immediately remapped it back to the same memory address, and that is where these discontinuities arise from.
Yeah, and suppose somewhere in the middle that process gets interrupted, like a crash or something.
All of the B tree nodes have stable copies on disk. So we do that. We actually do the same thing all the way up the tree back to these meta pages. If I need to modify a B tree node, and that B tree node is clean, then I need to copy that B tree node to another page on disk. Then update its parent node, which might not be dirty, so I have to dirty it. So in order to dirty a page, I have to dirty all the way up to the root. It's only 4, right? But I have to dirty all the way up to the root unless I actually hit a page that was already dirty.
Every time it gets dirty, it creates a copy that.
But the first time it gets dirty, it creates a copy.
Yeah.
And then we keep working on that copy
whenever
until
it
we see.
becomes undirty, then
Right.
like the old part gets.
And then we're doing this double buffering thing at the root, right? So if I crash in the middle of doing all of this, what I'll get is, because I never wrote to any of the pages in my snapshot, I can pull the last page out of the double buffer and there's a consistent snapshotted view on disk. There's all sorts of garbage distributed around it, but I can look through the B tree and I can get all of the good parts
And
that are part of that snapshot out of disk. Yeah.
Okay. Cool. Also, the 64 terabyte limitation is not some fundamental limit. It's because the offsets are 32-bit.
Well, they're 32-bit, but they're 32-bit.
They're 32-bit
16K
offsets
page
of
numbers.
16K pages.
Yeah.
So that
Which is
gives
2 to the 14 plus 2 to the 32.
Yeah.
you, right. Yeah.
So in theory, that could be lifted by extending that offset.
Right. In practice,
2 to the 46.
yeah. In
and then
practice,
only 2 to the 48.
CPUs right now
Or
use 2 to the 48, and one of those is your kernel versus sister. So you have 47 bits, and you've still got AF space for ASLR for your stack on one side and the heap on the other. So you want to use, you call it the middle half of virtual memory space, which is to say, like you have 25% on the low side, and then we use 50% for the PMA, and then 25% on the high side. So that's, so that's why it's offsets, right? Because we're adding, I've heard like 25% of the way in to these offsets that we're storing after we ship them over by 5, I think it is. For the, however much it is for a 16K page to recover a player. Yeah. And it's nice because it compresses your node size quite a bit.
Technically, we could double the effective storage space, but that's the limit with modern CPUs.
Yeah.
We could use 40 megabytes.
We could use the whole virtual memory space, but you would
we need
be
to
stepping on your stack and everything.
Yeah.
So, yeah. So like the constraint, the constraint basically is how much virtual memory can modern CPUs actually deal with, and everything lives in virtual memory.
Yeah.
If you want to go beyond this on current CPU architectures, you're going to have some idea of like archiving stuff that's not in virtual memory right now.
Writing a custom kernel.
And some, you don't quite have to go that far, but you're gonna be like saving stuff out to disk and behind the scenes, like serializing, deserializing, and fetching it.
Yeah.